Hi everyone. So I am just going to make a very simple video going through an example of what to do if you have two different populations and you're trying to make an inference about their means. So this is in particular very similar to a part of the project that I've assigned you guys. And in particular, I'm asking you guys in the project to try to make an inference about, do college students spend more time on homework for statistics than high school students do? Now, we did use as our part of our sample for the high school students, we did use some 11th graders. So technically they're not in statistics. But we're going to go ahead and compare the mean study times for each of those two groups and try to make a prediction about what do the samples say about a population. Now, the name of this kind of test that we're doing is called a two-sample t-test. The reason it's a t-test and not a z-test is because we actually don't know either standard deviations for either of the two populations that we're looking at. Now, I'm doing a question that's not about college students. I'm actually doing a question that's about pizza to make you hungry. But this particular question is a very good example of the same way that you would run the college student type question. So I'm hoping that this provides some information that is helpful to you guys. Now, for this particular question, we are wanting to look at Domino's Pizza and Papa John's Pizza, which are two very delicious pizzas in the United States, and I love both of them. But we want to see which one has more saturated fat content. You know, they say saturated fat's not good for you, right? So does Domino's have significantly higher mean saturated fat than Papa John's? What's the healthier option here? And so what I did is I collected, in this particular problem, 20 different pizzas. So I could actually count 1, 2, 3, 4, 5, 6, 7, 8. You get the picture. There's 20 different pizzas that I recorded the fat content in grams for. And for Papa John's, I did the same. Well, I only did 15. And that's actually okay. If you have two different populations, you can have two different sample sizes. Now, because the models are going to be different for each of these and what I look at, I'm going to have two different t-distributions I look at. Remember, a t-distribution changes based on your sample size. So for the t-distribution for Domino's, I'm going to be using one that has a number of degrees of freedom of 19. How did I find 19? Degrees of freedom is just one less than the sample size. So 20 minus 1 is 19. Same thing for the next one. Sample size is 15, which means the degrees of freedom I would use for this t-distribution would only be 14. Now, we don't need to know the degrees of freedom quite yet, but we are going to see that we're going to need this once we start solving the question. Now, what do you do first for any kind of test? Well, any good statistician knows that you've got to check to make sure that you can even run the test, and you do this by doing the conditions. Prior to doing the conditions, it's always healthy to set up your hypothesis. So let's go ahead and set up the hypotheses for both of these two tests. So the first hypothesis that I would look at is always going to be the null hypothesis. In particular, for these problems, we're talking about trying to make an inference about the population mean. And I'm going to use letters D for Domino's and P for Papa John to help me when I'm talking about this. So I want to know if one is higher than the other. So the null hypothesis always assumes that nothing is different. In other words, the null hypothesis says, so D for Domino's, the mean of the Domino's pizza's saturated fat content minus Papa John's is equal to 0. And I could write this out in words, of course. States that the true, instead of population proportion, we're going to say here the true population mean. And now remember, we're talking about differences, so we do want to sneak the word difference in somewhere. So the true population difference in means, I'm going to add that word right here. Okay, of saturated fat content and Domino's and Papa John's pizzas is 0. Now, what's another way I could say this? I could say that the null hypothesis states that there will be no difference in the true population means between the two pizzas. So there's different ways that we can say that basically the null hypothesis is assuming that they have the same type of saturated fat content. All right, now let's go on to the alternative hypothesis. And the alternative hypothesis is different because we're trying to prove that Domino's is higher. So not just different, but that Domino's actually has more unhealthy fat in their pizzas. So I would say D minus P is not equal to, nope, I'm actually going to draw a greater than sign. That it's actually, if I were to subtract the two, I would get a positive number. Remember that another way that I could say this is that this is greater than that. The only thing is that generally speaking on an AP test, they're going to write it the first way instead of this second way. So I'm just going to put this in parentheses to remind you that that's what it means. Okay, so the alternative hypothesis states that the true population difference in means. Another way you could say this would be the true difference in population means. That would also work, and actually that might even be a slightly better way of saying it, to be honest. Of saturated fat content in Domino's and Papa John pizza is, okay, is higher. The difference is higher, or we could say is positive. So that might actually be a better word to say here, is positive in favor of Domino's. Another way you could say this, if you wanted to come up with another way, we could say that we're assuming that the if I were to do Domino's population mean minus Papa John's population mean, I would get a number that's positive. In other words, the population mean for one is greater than the population mean for the other. Okay? Now, we're going to go on to the conditions now. Okay, so the conditions. Anytime you have two populations, you have to do 9 conditions, right? I'm not going to write them all out. I'm sorry, okay? But I am going to talk through all of them for sure. So the first population we want to look at is Domino's. Whoops. Okay? And remember, we're using D to talk about the Domino's mean, okay? So the first thing I could check would be independence. Okay, so are my Domino's pizzas independent of each other? Actually, our problem doesn't say. So we just have to kind of, well, I'm sorry, not independence. Sorry, independence. We can't assume that. So okay, or we could say, I assume that the Domino's pizzas are independent of each other. Now, I'm just gonna go ahead and write this down. So this is the Papa John's. And this is gonna be represented by P. So independence here, okay, is gonna be the same thing, but I'm gonna say, I assume Papa John's pizzas are independent of each other. Cool. Okay, let's go ahead and go on to randomization. Okay, so for randomization, basically, we could write, I'm gonna not write the same thing in the other column. I would like for you to go ahead and write it though. So for randomization, this is the one that it doesn't say in the problem. It doesn't say that they were randomly selected. We're gonna go ahead and assume that they are a representative sample, okay? I can assume that this sample of Domino's pizzas are representative. And then you would say the same thing about the Papa John pizzas. So not the exact same thing, but make sure you change it to saying the word Papa John. Now let's look at 10%. Okay? I'm going to assume that my sample sizes are indeed less than or equal to 10% of all pizzas by Domino's. Okay, so for this one, I could say 20 pizzas. This is my Domino's pizzas are less than or equal to 10% of all Domino's pizzas. Not all pizzas, but specifically all pizzas that are produced from Domino's. And then I could say the same here, 10% rule tells me that the 15 pizzas are less than or equal to 10% of all pizzas from Papa John's. All right, moving on to our last but certainly not least, because we're looking at means, we're gonna need to do the nearly normal condition. So I'm gonna go to nearly normal. Now, the cool thing about the nearly normal condition is that if your sample size is greater than 30, you get to use the central limit theorem. And you can say the central limit theorem guarantees that I can use the sampling distribution will be nearly normal, right? Because my two sample sizes here are actually less than 30, I'm gonna have to do something a little bit trickier. So my nearly normal condition would actually tell me that the sample size, n, okay, is 20, which is less than 30. Sad face. What that means is that I need to sneak a look at a box plot. So I'm gonna go ahead and put in a box plot here. I'm just gonna draw a little bit of a label on like what my box plot is going to look like. Okay, so the box plot, I would need to add all of my data into my calculator to look at. So I want you to go ahead and take it. I'm actually going to go ahead and do this right now, but maybe you can pause the video and also do the same. But I'm just going to go over here to my stat edit. And it looks like my list 1 and list 2 are already cleared. In list 1, I'm going to go ahead and do all of my Domino's pizza fat. Yummy. And at the very end of this, I might want to just go back and make sure that I've put it all in correct. Because, you know, we try to be perfect, but sometimes we're not. Okay, looks like I clicked enter after my last one, so I've got, let's go all the way back to the top, reading them out. I've got 17, 12, 10, 8, 8, 10, 10, 5, 16, 16, 8, 12, 12, sorry, 12, 15, 7, 11, 11, 13, 13, 11, 12. Okay, I'm going to do the next ones a little bit faster, but you should also be going back and double checking because that's just a good mathematical skill. And it looks like I'm at the right amount of samples sizes, or samples, yeah, for my list 2. Okay, so to find a box plot, you're going to go to stat plot, go to the first plot, go to this option for your, sorry, for this, you're going to go to list 1, go to graph. You're going to probably need to hit zoom 9 so that you have the stat graph. Okay, if you click trace, you should be able to trace through to get your 5-number summary here. Okay, so I'm gonna go ahead and write all the stuff I need to know here. I'm gonna go ahead and do its grams is my unit. So remember, you always wanna do a title label tick, tick, tick for any kind of plot. So a box plot is gonna be you can title it box plot. If you want to title it box plot of Domino's pizza sample, you can, but this is the grams, okay? So if I go to trace on my calculator, which is right here, that's gonna actually take me straight to my minimum. And you're just gonna do the 5-number summary. So you're gonna do your minimum, okay? And that's at 5. Then you're gonna arrow over Q1, that's at 9. You're gonna try to kind of space it like it would be. So try to make it as proportional as possible. This is 11. This is 13. And the last number is at 17. So it's a little further away. Okay. All you gotta do now is connect your dots. So I'm gonna draw my box. Boom. Okay. Now, what can you tell me based on this box plot? Well, you could tell me a lot from a box plot. Like you could tell me that this looks pretty symmetric. You could also tell me that there's no outliers. And we would also see what the center is. So there's a lot, but you can't tell me the shape. You can't tell me if it's bimodal or unimodal. So we are going to take just a very quick sneak peek. Going back to stat plot, we're going to just look for just a second at the histogram to make sure that there's not two bins in it. Okay, so I'm going to go over to that, go back to this. Okay, so I could go back to Zoom 9. Oh gosh, graph, Zoom 9. Okay, so what can you tell me? Yeah, it looks like there's only one big peak, right? I mean, yeah, there's a little peak, you could argue that, but for the most part, it looks unimodal. So that's great news, okay? Because that's gonna help me out here when I talk about this, okay? So I could say that this graph shows that the sample distribution, because this is based on a sample, is roughly symmetric. So it's never going to be, use a wiggle word when you talk about symmetry. It's never going to be exactly symmetric. Unimodal. Okay. With no outliers. Okay. So we've got the shape. We've got symmetry, no outliers. Okay, so let's also check this one just to make sure to see if we can still use a normal distribution. That's really what we're trying to see is, does a normal distribution, would that be the best distribution to mimic this? So I'm still gonna check the nearly normal condition on this side as well for this box plot, okay? So again, my sample size is not big enough, sad face. We're gonna get our box plot going for this. The cool thing is I've already put my data in for this. Remember, we already did list 2. So all you've got to do now is come back over to stat plot, change it back to the box plot, change this to list 2. Be careful not to accidentally draw the same box plot again. And then we're gonna do Zoom 9. Okay. This one looks a little bit like a bigger one. Okay, so here we've got grams. Here we've got our box plot for, and we've already very well labeled that this side is talking about Papa John, but if you wanted to say Papa John pizza box plot, that would be even probably better than what I'm doing. So I've got my trace button, and we're just gonna very quickly label this. So this is 3, 4, jumping over to 6, jumping way over to 9, and our last point is also at 11. Again, this is called the 5-number summary when you talk about your Q1 and your min and your max and your Q3 and the median. Okay, so we do want to check for shape real quick. So let's go back to our histogram. We're going to change this to histogram. We're going to go to graph, and we're going to go zoom 9 again. Okay, now this is kind of an interesting histogram, right? But there's nothing to tell me that it's bimodal, okay? So I'm gonna go ahead and safely kind of walk forward with this, even though it's not the best shape. This still kind of tells me that most of the data is at least centered there, okay? So I'm gonna say the same, okay? So the sample distribution for Papa John pizzas is roughly symmetric, unimodal, we think, with no outliers. Okay, now because of this, okay, I'm going to say because, and I could actually say since both of these are, because both box plots show these qualities, both sampling. So remember, we always use sampling distributions. Both of the sampling distributions are nearly normal. Great. And let's not forget our number 9 condition. So number 9, and that is we want to make sure that our pizza chains are independent of each other, okay? So number 9 is the independent group assumption. And that is, I can assume that Domino's and Papa John's pizzas are independent chains. You could say pizza chains, right? Great. Okay, now that is just the conditions part of this. The nice thing is that now that we've got everything set up, it's actually going to be pretty easy to go ahead and go forward with the actual hypothesis test. So after conditions, we move on to mechanics. And the nice thing is we get to do all of this in the calculator, which is great. So let's go over to mechanics. Okay. So my mechanics is what I'm going to do is I'm going to go ahead and start off by coming over here to my calculator. And I just want to show you guys where this is found, okay? So what I'm going to do is I'm going to go to, remember, we've decided that we're doing D minus P, okay? So if the numbers are positive, that's telling me that the difference is positive, which means Domino's is higher. If I get negative numbers, that's telling me that the Papa John's is actually higher. So we're going to come to stat, test, and this is a 2-sample t-test. That's actually what we named it at the beginning of this. So a 2-sample t-test, okay? And before I move on to my mechanics, there is a statement I need to make sure I do, and I should actually do this after my conditions. Since all conditions are met, I can calculate a 2-sample t-test, and that's where I'm going to name it. So that's how the AP takers are going to know what test I'm doing in the calculator. Now, I definitely use data for this one because I entered all my data in, and that's how you're going to do your project too. So list 1 is my Domino's pizza. That's perfect. List 2 is my Papa John's pizza. Very good. Frequency only happens once. We want it to be a greater than sign. Now, I want to know, is this pooled or is it not pooled? Okay, so let's just check real quick to see what does the pooled, what kind of numbers do we get here? Okay, so notice that the t-score for this one is 4.67. Let's see if we get a different answer when we do not pooled. 4.67 versus not pooled. Let's go to calculate. 4.823. Okay, now notice I said not pooled. Now for proportions, you pretty much always pool them for these for the sake of our class. For samples, it's a different story. You're usually going to not pool together samples, and the reason is that you want to actually assume that they are different from each other, right? We want to assume that for this particular problem, the fat content of one is different than the fat content of another, and they don't come from the same population. The populations are not the same that we're taking them from. So we can't throw them all in the pool together. I'm taking pizzas from one location for this first one and then pizzas from another location for the other sample. So my sample is not coming from the same population, and therefore we have to, for samples, for the sake of samples, you will usually, when we're talking about means, you will usually not pool them together, okay? So let's go ahead and let's copy down these statistics, okay? So I'm just gonna make a note of that this is not pooled. And I'm just gonna copy down everything that's in my calculator now. Notice that my calculator uses 1 and 2. We use D and P. So please make sure that as you're copying this down, your calculator mechanics, really the only thing you need to make sure you do is don't forget the degrees of freedom, but also don't forget to change your variables to reflect what you did in the problem. So this T right here is talking about my t-score. So I'm just gonna copy it down. The t-score is 4.823. The P, this is talking about my p-value, is 1.5756, if I want to round a little bit on that, times, don't forget this little e down here. Look at this. This actually means it's really tiny, times 10 to the negative 5th power. So let me just show you what this number looks like. This number looks like this. That's actually a very small p-value. If you forget to notice that that negative is there, you're going to think that it's a really big p-value. So be careful. My degrees of freedom for the whole problem is 32.75. Now, what is this degrees of freedom? This is they took the degrees of freedom and they combined them, okay? There's a formula for it. I'm not going to get to go into it this year, unfortunately, but you can definitely look up how do you find a pooled degrees of freedom. Now let's continue copying down all of our statistics that they give us. So mean of 1 is the same as mean of D. So my mean fat content for D is 11.25 grams. My mean for, what's the other one? The other one is P, Papa John's pizza, is going to be 6.53 grams. My standard deviations, I'm just going to write those out here, which is S. I'm going to write SD, 3.19. And my SP, standard deviation, is 2.5875. Okay, now I could also write my N's. So my N sample sizes, N is 20. Don't forget your DF, that's an important thing, is 19. And here is 15, DF is 14. And those are all of my calculator mechanics that you could just do instead of doing it all by hand to make it nice and easy. The last part is the conclusion, and then we are done. So the conclusion is just like what we've done before. So the conclusion, basically what we're going to say is, using a two-sample t-test, my p-value of, let's see what that was. Oh, it was so tiny, 0.00015 is less than, we're always going to assume that our alpha level, unless it's given to us, is 0.05. I will reject the HO since my P was low. Okay. Okay, now remember, if you are rejecting the null hypothesis, then that means you have evidence. So let's answer the question, is there evidence of this? There is evidence to conclude, let's go back to our alternative hypothesis, that the true difference in population mean fat content between, I'm changing the wording a little bit here, I'm actually making it a little bit better, that's why, but I could just copy exactly what I wrote for my alternative hypothesis. The true difference in population mean fat contents between Domino's and Papa John's Pizza is positive. Okay. In favor of Domino's. That just means that the Domino's is greater. So now let's actually translate this into what we're talking about, okay? So there is evidence. I'm just going to answer the original question to conclude that Domino's has significantly higher mean saturated, I'm going back to the original problem and just copying it, fat content than Papa John's Pizza. So I literally just copied the last sentence of that problem. So that's my conclusion for this problem. And one thing that's interesting to note is that, and this is just a parallel to y'all's project, that in your project, when you're doing this, you're going to be thinking to yourself, which one is higher? So if your whole hypothesis is to prove that college students study more, and you see that there is a difference, and you see that there is indeed, a positive number, then what you're going to say is that, yeah, college students did study more. I got, a positive number here, mostly positive numbers when I subtracted the two, versus if you might get something different, right? And so please think about the parallels between this problem, because it's actually very similar to the type of project problem that you're going to be doing. I hope this was super helpful, and please feel free to ask me if you have any other questions regarding any parts of this problem. Thanks, and have a wonderful rest of your day. Bye-bye.